So some definitions. If we have just a little tiny box, and we'll actually be playing with these, if they're filled in, it's worth +1, and if they're not filled in, it's worth -1. And one rule is if you ever combine a +1 and a -1 together, well, if you combine those mathematically together, you would make a 0. And if I extend this to a piece that looks like a rectangle, and I fill in the rectangle, I call that a positive x. If I don't fill in the rectangle, I call it a negative x. And if you combined those two together, you would end up with no x's. Another shape that we will be using this year will be x in each direction, and it'll look like a square that's filled in. And that will be called an x squared. If I have one of these squares but I don't fill it in, it'll be a negative x squared. One of the things you can quite quickly see with these algebra tiles is they're different shapes. I've got these little tiny boxes, I've got these rectangles, and then these rectangles are actually, they would fit perfectly along these sides. So I could actually fit a rectangle here, and I could fit a rectangle here, which I won't do, but it creates this perfect box. It's x by x, which in geometry, x times x is x squared, so that's what this would look like, is a square, x squared. So then we can start to ask questions, well, what would 3x look like? And we can start to model that. Well, 3x would look like you'd need a positive x, which would be filled in like this, and another positive x, and another positive x. And how would that differ than, say, x plus 3? Well, x plus 3 would only need one of these x's, kind of these bars, and then it would need +1, +2, +3 little integer chips. And you can start to model all sorts of interesting algebra just by, there's an x squared, and an x squared, minus, just leave it white, minus, and then +2. And we'll be practicing that when we get to class. Now, as I was saying, the geometry, the shapes of these different algebra things, like an x looks the same as an x, but it looks quite different than an x squared. Those shapes give us an idea of our next concept, which is our last concept, called like terms. Like terms are terms that have the same variables raised to the same exponents. So xy squared would be a like term with y squared x, because they both have an x and they both have a y times another y. Now generally we use alphabetical order within one of these terms, so we don't usually write, well, we never do write y squared x. We would always write that as xy squared. And it's a little easier to see that those are exactly the same pieces of algebra. Whereas a not like term might be like 2xy cubed and 2x cubed y. Well, you don't even really need to think about the coefficients. We're just looking at the variable parts. But this is x to the 1. This isn't x to the 1, this is x cubed. So those are not that they're not equal, they're not like terms. And the cool thing with like terms is that you can combine them together. So if you have 3x and you have 5x, well, you've got 3 of those bars combined with 5 of the same shape. And hopefully you can see that altogether you have 8 of those little bars. Whereas not like terms, like x squared plus an x, well, this is a big square, and this is a rectangle. Those aren't the same shape, so you can't combine them together. If you're counting these shapes, at least they're all the same shape, and you can combine them together. So you can combine together like terms. But if they're different shapes, you can't combine them, you can't count them and say, oh, I have a certain number of these square rectangles. You either have squares or you have rectangles. So every polynomial term has a different shape to it. And if you really remember that, you won't have much problem with combining together like terms. Okay, that's it for today.